again, thank you for coming. The first presentation today is Dynacast high pressure die casting. The presentation will be given by Mr. Sparkman. He's the engineering manager of our Elgin, Illinois plant. Again, my name is Ed Oliva, and I'm with Dynacast International. We're a global die casting company with 17 plants in, actually 21 plants in 17 countries. So, Tim, I think we only got 20 minutes, so we'll start the presentation. And if there's any questions, I'd like to make this a very interactive thing. So if you see anything in the slides that you have a question about or you want to ask or have Tim stop and explain a little more, please just let us know. We're going to try to be as technical as possible and as brief and concise as possible. Thank you.
Good morning, everyone. The presentation that we're going to give to you is going to be a condensed version. If any of you are interested, this is actually a seminar that lasts about an hour to hour and a half. We would be happy to talk with you afterwards, to come to your plants and actually give a presentation. This is generally designed for engineers and procurement people. I'd like to start off a little bit, again, with our timing here of die casting, kind of a die casting 101, and talk a little bit about what die casting actually is. To talk about die casting, let's talk about the equipment first. There's two different forms of casting machines. You have hot chamber and you have cold chamber. Cold chamber, if you're familiar with an injection molding machine, is very similar. You have a movable platen, you have a fixed platen. Unlike on a plastics machine where you would have your nozzle and your heater bands and that, fill in the resin, typically a cold chamber machine is used for aluminum die casting. You have a furnace or a central melt system. In this case here, it's illustrating that you would have say a furnace that's alongside the machine. Molten aluminum would be along, it would be around 1240 degrees Fahrenheit. It gets scooped up in a ladle, gets poured into what they call a shot sleeve, and then gets injected into the die. And you can see a video here of the actual, that's the ladle, poured into the shot sleeve, gets injected, the casting is made. The robotic arm comes in, extracts the casting out, a die loop spray mist comes down, sprays mold release for the next shot, and it continues. The other version is a hot chamber. A hot chamber typically is designed for zinc and magnesium die castings. Same principle as a cold chamber, with the exception here that the gooseneck in the injection system is actually submerged in the molten zinc. The zinc is about 740 degrees Fahrenheit for its melting phase on that. And basically what happens there would be like if you took a syringe underwater, pulled back the plunger, material fills in, and it gets plunged, or the plunger comes forward, injects the zinc or say magnesium again from a hot chamber into the casting die. These casting machines range typically in the industry from about 100 metric ton and can go up to several thousand tons of clamping force. Cycle speeds on these machines typically will range anywhere from 20 seconds to a few minutes. If you're doing transmission blocks or large components, you could have a cycle speed of anywhere from, say, 3 to 5 or 6 minutes, depending on some very large castings. Now, Dynacast, our core competency is really our force slide, which I'll show you next. But typically the castings that Dynacast produces are parts that fit in the palm of your hand. Like a small dinner-sized plate from a size standpoint. Now, what's unique to Dynacast and a different type of machine that's out in the industry is what we call the force slide. There's two different types of force slide. There's a Dynacast and also a Techmeyer. Techmeyer is actually owned and operated by Dynacast, but we do sell the equipment on the open market, again, branded as Techmeyer. Now, in a force slide, very small footprint. These machines are designed and built by Dynacast. They're made in our German facility. And as Ed indicated before, the 21 different plants that we have, all the Dynacast plants have this equipment worldwide. To show you a quick picture here, this is a video of the force slide running. These machines run anywhere from, say, 15 cycles per minute up to 100 cycles. We can run single cavity and also multi-cavity castings. These parts are generally under 170 grams as far as shot weight. Basically a quarter of a pound casting or less. Very, very fast speeds, very tight tolerances, which we'll get into in a moment. Now that we talked a little bit about some of the equipment, let's talk about the alloys that are out there. On the zinc side of the materials, there's a kind of a wide range of different alloys to choose from. Now you'll see on the bottom left corner of Dynacast.com, there's a lot of information up there that you can go onto. You can look at the tensile strength, the mechanical properties of the different types of alloys. Generally speaking, Zamac number 3 is probably the biggest material user. It's generally the workhorse in the industry. Now, one thing that's unique or nice about the zinc alloys, maybe compared to a plastics, is the shrink factor is the same. If some of you have a plastics background, if you're dealing with nylons, polypropylene, all those different resins have different shrink factors. The shrink factor for zinc is typically 7 thousandths per inch. So if you wanted to spec something out that you wanted to, say, maybe use Zamac number 7 for crimping purposes, if you want to do orbital riveting, do a lot of different connectors where maybe you want to take your component, put it together, have a very thin wall, and come in and orbital rivet the outside walls to retain that part. Zamac 7 would be an ideal candidate. But if you're looking for stronger parts, maybe you'd want to go to a Zamac number 2. Ideally here, you can switch the materials and it would not affect the casting die as far as the outcome on the parts dimensionally. You also see that there's an AccuZinc 5 on the bottom. That's actually a General Motors patented material that Dynacast is licensed to use. And this material is primarily used for enhancement against creep. Zinc will have a tendency to creep. And again, Zamac AccuZinc 5 is a good candidate for that. There's another material that's out in the industry that just came on the market in about the last 18 months. It's called EZAC. Excuse me. It's made by Eastern Alloys. And again, it's got some superior mechanical properties and also is very good for creep resistance. Some of the different materials that you have in the aluminum would be aluminum 380, 383, and also ZA27. Magnesium, typically in the industry would be AZ91D. Now again, Dynacast, we do run all three of these alloys, zinc, aluminum, and magnesium. I'm going to show you a brief illustration here of just the yield strength when you compare zinc to some of the brass and the steels out in the market. Probably about 50% of the business that Dynacast pursues are parts that were never designed as a die casting. They're either conversion parts from either plastics, stampings, screw machine parts, and usually a combination of taking several parts and combining them for a value added, looking at taking cost out of a product, maybe combining a stamping part along with a plastic and making it one casting. So far we've talked about the machines, we've talked about the different alloys that run in the machines. Let's talk a little bit how we get there as far as kicking off a program. On Dynacast, it starts with running Pro Engineer. We run Pro-E across the board on all plants. Every part that we basically kick off, we would redesign your part in Pro-E if it's not a native file. And the reason we do that is so that we can address draft angles, radii, look at putting enhancements into your part. If it's a screw machine part, we'll look at putting weight savers possibly into the part, where you need to hold tight tolerances, any GDT characteristics. So we'll design that part with your cooperation, make a 3D model, and start from the design. All our designs start from the model into the 3D of the casting die. Once we've got the model and casting die, we'll run a mold flow simulation. Now, mold flow simulation basically does a few things. We can show the velocity of the material, we can show air entrapment, and also solidification. What you're seeing here is actually the velocity. This is a 4-cavity die, and it has a pin gate, and basically what you're seeing is that it's filling a blind area, which is the shaft within the part that has no parting line on it. Another utility that we run is a thermal analysis by the software we use is MagnaSoft. Here we can analyze hot spots within the tool or within a casting so we can address any type of bubblers, cascades, anything like that that we need to address on the casting. Now, once we've got the tool and everything figured out, we have to look at the gating. The gating, one of the tools that we have is called PQ squared. That's pressure and volume. Some of the things that you look for in a casting would be the gate velocity. Zinc and aluminum typically run between 1,000 and 1,600 inches per second as far as the velocity. The material, I mean, basically at that point, it's flying in there, again, up to 1,600 inches. You can go on thin wall parts that are high cosmetic that you can actually start pushing up to 18 to 2,000 inches per second. Our fill times tend to be about a quarter of a millisecond or a quarter of a second from a fill time. Static pressure that we typically look at is about 3,500 psi. You have accumulators that are on the machines, and we can actually start to see anywhere from 8 to 10,000 pounds per square inch as far as the metal pressure that you have within a casting die itself. The PQ squared software allows us to analyze with our process engineers those parameters as far as looking at our gating, looking at the velocity of the material, looking at the static pressure that we're going to have. And what it does is it creates this green envelope that you see that allows the process engineer to make fine-tuned adjustments and still be with an operating part for the die. One thing that we try to achieve on a die casting is what we call atomization. When the material actually flows in through the gate into the cavity, which is producing the part, you're looking at atomization. It'd be like if you took your perfume bottle and you have a bunch of little mists and droplets that you're trying to achieve from a filling standpoint. Another tool that we have is a finite element analysis. Again, I had mentioned earlier that a majority of the parts that we do are parts that were never designed as a die casting. So we use this tool for, looking at comparison for plastics, for steel, screw machine parts, those types of things. Now that we have a design done, we get into the tool build. Now, talking about a little bit on the build, we've got 3 different centers of excellence throughout the world. One's in Europe, United States, and also in Singapore. Our United States plant, we have a tooling division that's in Germantown, Wisconsin, just northwest of Milwaukee. We've got about 30 tool makers located up there. These center of excellences are designed strictly to help and support the Dynacast plants. Talk about lead times a little bit on our 4th slide, which you saw earlier. 4 to 5 week lead times for design and build. Conventional can be anywhere from 8 to 10 weeks. Some of the things that we do is high-speed milling. The cavity blocks, we can actually heat treat and harden the dies themselves and actually go in there with a high-speed mill and cut the cavity detail right in a solid piece of steel without using electrodes on that detail. Secondary operations, some of the different items that you have from that standpoint would be secondary machining, tapping, reaming, milling, those types of things. But we, as a company, we work very hard with our customers to try to reduce those costs by possibly looking at self-tapping screws opposed to tapping. If you're looking at assembling 2 different parts together, maybe orbital riveting where we cast a post so that you can interlock a part and come in and stake a part. Some of the different things on finishings, you've got different types of platings that can be applied to the castings. Most of the platings today are all RoHS compliant. Some of the economics on the lower end would be your trivalents. There's zinc, yellow, clear, olive drab, those types that can give you some superior salt spray protection, ranging anywhere from, say, 48 hours to 248 hours of salt spray protection. When you move up the chain a little bit on salt spray requirements, you can go into E-coats and powder coats. There's chrome plating, there's Teflon, a lot of different applications that you can use from a die casting. Also, from an assembly standpoint, we do contract work as far as making a casting. If you want to have that fitted onto an O-ring or something of that nature, we can also look at doing that. And also what's unique to Dynacast is our IMA process, which is injection molded assembly, where we can actually take a die casting, and let's say you need to have a screw or for a thread and you need it to be steel for some reason for a requirement. We can actually mold both those parts together, and that's another service that we offer. Again, trying to cut down on time here a little bit. Just wanted to give you a quick rundown, a little bit again about the machines, the different alloys, our equipment, and what I'd like to do is show you a couple case studies so that we can talk about some of the options that we have that are available. And I'm just going to show you this one right here. This is a part that was actually 6 different castings we consolidated into one die casting. You had screw machine parts, you had an extrusion part, and you also had a stamping. The customer was actually brazing these parts together. We worked with them. We created one die casting. This part gets electroless nickel plated, and it saved the company a tremendous amount of money. It helps to reduce and consolidate their componentries and also some of the quality sides of things. Are there any questions at this point? We still have 5 minutes? Oh, well, we're doing all right then. Maybe we can get back into a couple other things here. Let me back up a little bit. Let's talk about, on the fourth slide, again, this is a video of our Elgin facility showing our 4-slide equipment. Very fast production rates, as I mentioned earlier. These machines run anywhere from 15 to 100 cycles per minute. Very tight tolerances. Thin wall construction, we can get down as low as 10 to 15 thousandths of an inch wall sections. And again, we look at eliminating as much secondary operations as possible. Some of the tolerances that we actually hold on inside diameters, we can hold at plus or minus 5/10 thousandths of an inch or 5/10 on very short distances. Again, we talked about the wall sections. You see on the very bottom there, down to about 15 thousandths. We can actually get down sometimes in 8 to 10 thousandths in certain areas also. Core draft angles, you can go back as minimal down to 0 degrees for very short distances, and then say 1.5 to 2 degrees thereafter from a casting standpoint. There's the NATCA standard. Some of you may or may not be aware of NATCA. It's the North American Die Casting Association. The headquarters is located here in Rosemont, Illinois, just east of O'Hare Airport. They publish a NATCA standard precision or a NATCA standard and also a precision, where you can see that on the Dynacast side, our equipment and our tooling can yield a lot tighter tolerances than what you would typically see in the industry. On the conventional die casting, very similar. We do run conventional machines, so we can run castings up to about 2 pounds. Very tight control on CPK values. From a standard deviation, we typically look about 2 to 3 10,000ths of an inch. So basically what we're saying on that is if we see a tolerance zone of 0.1 millimeters or 4 thousandths total tolerance, we can nail a 1.67 CPK value typically. Some of the tolerances on conventional are a little bit wider. As you can see, inside diameters go up to about plus or minus 1 thousandths of an inch. Core diameters, we definitely look at about a half degrees draft per surface on that, and cavity dimensions are about 1/4 of a degree. And again, we'll do a slight comparison here for the Dynacast process compared to what's typically standard out in the industry. Okay. And really, ladies and gentlemen, that's kind of a die casting 101. I'm trying to keep this as brief as we possibly can to keep us on time. Ed, would you like to part with any? Okay. Again, if anyone would like to have this presentation, again, this presentation generally takes about an hour to an hour and a half to give. Would be happy to come to your facility. A lot of times we do a lunch and learn. If you want to have, during lunch, we can come to your plant and go through this in more detail, talk about any projects that you folks might have, and we'd be happy to review that. And we do have plants throughout the area, so that, okay? And again, we're here in Elgin. Some of you might be visiting the Chicagoland area. We're just about 35, 40 minutes away from here. If anybody would like to come to visit the plant while you're here in Chicago, let us know at the end of this, and we'll be happy to coordinate that and accommodate you, okay? Thank you, everyone.